Okay, thanks. You can mute your mic. So, good morning, everybody. Good afternoon. So I'll just start by taking some of the questions in the form, in the feedback form. There weren't too many questions there, but there were a couple of interesting questions. So maybe I'll start with the simplest question, which is from Amit Kapas, and the question is find the number of orbits under the action of the cyclic group 1356 acting on 8 elements. So let me just write down the question. So we have this 1, 3, 5, 6. So what does this mean? So we have 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. And what this cycle does is it takes 1 to 3, 3 to 5, 5 to 6, and 6 to 1. And all these remaining elements, 2 goes to 2, 4 goes to 4, 7 goes to 7, and 8 goes to 8. So this is the cycle notation of this permutation. It takes 1 to 3, 2 to 2, 3 to 5, 4 to 4, 5 to 6, 6 to 1, 7 to 7, and 8 to 8. So just to review, some of you had some confusion between cycle notation and one-line notation. So this is the cycle notation. Usually you leave out the one cycles, and the one-line notation here would be 1 goes to 3, 2 goes to 2, 3 goes to 5, 4 goes to 4, 5 goes to 6, 6 goes to 1, 7 goes to 7, and 8 goes to 8. So in this cycle notation, it's much easier to see what is happening with this permutation. The one-line notation doesn't really show that so obviously. But we've been using one-line notation for most of our calculations just because in some settings it's a little there's some features which you can see from the one-line notation and some features which you can see from the cycle notation. Okay, so the question that Amit asked is you take this 4 cycle 1, 3, 5, 6, and that generates a group. So that generates a subgroup. So you can take this, let's call this element X, and you have a subgroup that it generates. It consists of 4 elements, 1, x, x squared, and x cubed. And x to the power 4 will again be the identity element. So the question is, what are the orbits of this group? So let's call this G. So G is a subgroup of S8, and so G acts on the set 8. And you can see the orbits very clearly from this. If you apply, if you take the orbit of 1, it will contain 3 because x takes 1 to 3, and it will also contain 5 because x squared takes 1 to 5. And it will contain 6 because x cubed takes 1 to 6. And of course, it will contain 1 because identity takes 1 to 1. So the orbits are so there's one orbit which is 1, 3, 5, 6, and then the remaining elements are in singleton orbits. Because if you take any power of x, it will just take 2 to 2 because x takes 2 to 2, and 4 to 4, and 7 to 7, and 8 to 8. So there's one more orbit which is 2, another orbit which is 4, another orbit which is 7, and another orbit which is 8. So this is how you can compute the orbit of the subgroup generated by this 4 cycle on 1 to 8. So I hope that answers your question. Yeah. So, yeah. Anuj Shukla says clear nahi dikh raha hai, but I don't know. Can most people see what's happening? Okay. So I can't do anything about the thing now. So let's go on to some more questions which are already on the which were submitted in the form. And as I said, there were not too many questions there. So so there was one question about so Devopam Ghosh. He requested a discussion of Drazen inverse and Moore-Penrose inverses, common features and contrasting properties. Now, these are inverses which are not really very interesting in the context of group theory. Let me explain why. So maybe I won't talk about specifically Drazen inverses or Moore-Penrose inverse. Let me just talk about this notion of a generalized inverse. So if A is a matrix, then a generalized inverse of A is a matrix sometimes denoted by A plus such that A plus A is equal to A. So this is a definition that comes up when you study matrices, and it's quite important in statistics. Now the thing is, there's a difference between matrices and groups. So first thing to note is that if you take n by n matrices over R, this is not a group, right? Because there are matrices which don't have. This is not a group under multiplication. Of course, it's a group under addition, but here the operation that we're using here is matrix multiplication. So it's not a group under matrix multiplication. And the reason is, of course, that not all matrices have inverses. So in general, the thing is that in this structure of n by n matrices, which is called a ring, there isn't always a notion of inverse, and this is why people have tried to find something that is as close to an inverse as you can get. And the Moore-Penrose inverse is one such, and the Drazen inverse is another. The Moore-Penrose inverse, even if you don't know what it is, don't worry. It's a special case of what I've written up here, a generalized inverse. So, but in the context of groups, you can make a similar definition. So let's just say this. So let G be a group. And let's take X in G. Suppose we say that X plus is a generalized inverse of X if X plus X is equal to X. But this is not at all going to give you anything new in a group, because if X plus X is equal to X, you can multiply both sides on the right by X inverse, and you'll get X plus X inverse is X inverse, which means that this X inverse cancels out, and here you get identity. So what you get is X plus is the identity, which means that X plus is X inverse. So these kind of generalized inverses, or the Drazen inverse is not really a generalized inverse. These do not give you any new concepts in the context of groups. However, they do give you very interesting things in rings in general and especially in matrices. But I won't go any deeper into these because it's not really pertinent to this part of the course. Okay, so then there was one very interesting question. Frankly, I'm not sure exactly how to answer it. So let me just read out this question. So where did it go? Okay, so this question is from Kavita, and Kavita says, as we know, symmetric groups on n letters has a subgroup H which is isomorphic to the symmetric group on n minus 1 letters. Also, H is not necessarily a normal subgroup of Sn. And we have counterexamples for that. In fact, we know that Sn has only one proper normal subgroup, that is An for n greater than 4, and two normal subgroups for n equals 4 and so on. The question that she asks is, in general, how to prove that H can never be a normal subgroup of Sn for n greater than or equal greater than 2. So what she's asking is, we have this group Sn. Let me just, yeah. So we have the group Sn, and we want a subgroup H of Sn such that, okay, so we want H as a subgroup. H is isomorphic to Sn minus 1. And thirdly, that H is normal. And her guess is that this cannot happen, and she wants to know why. So one thing is, okay, so you cannot do this. And the reason is basically that, we know, as she herself pointed out, that, okay, so there's this famous theorem. So as you know, Sn has a subgroup An called the alternating group, which I defined using matrices. You just take the determinant of a matrix associated to the element of Sn, and if that determinant is +1, then you're in the alternating group. And then there's a famous theorem that An has no proper non-trivial normal subgroups for n greater than or equal to 5. I'm not going to prove this theorem. I'm not prepared to do that. It takes a little bit of work. But of course, we know the conjugacy classes in Sn, and that almost tells us what the conjugacy classes in An are. And using that, you can try to show that An has no proper non-trivial subgroups. So the only normal subgroup of Sn is An. So obviously, Sn minus 1 cannot be a normal subgroup of Sn. But then again, is there a simpler proof of this fact that if you have a subgroup of Sn that's isomorphic to Sn minus 1, then it cannot be normal? Well, I didn't have enough time to think about this, so I don't really have a quick answer. If I come up with a nice answer, I'll let you know. But there is something very interesting. So so usually how do we think of Sn minus 1 as a subgroup of Sn? So usually we think of Sn minus 1 as is a subgroup of Sn. It acts on n by permuting the elements of, permuting the first n minus 1 elements. And this makes Sn minus 1. So you can think of this Sn minus 1 as sigma belongs to Sn such that sigma n is equal to n. So that would be permuting the first n minus 1 elements. So here you have an action of Sn on n elements, and this action is transitive in the sense the orbit of any element contains all the other elements. Because, for example, using an n cycle, you can take 1 to 2, 2 to 3, or to anything you like. So that's. But here's a very interesting example where there is an action. So this action of Sn minus 1 on n is not transitive, because you cannot take anything other than n to n. It is a transitive action of S5 on the set 1, 2, 3, 4, 5, 6. And this is a very interesting action. What you do is, so S5 has 24 5 cycles. I'll let you think about that. And each 5 cycle is contained in a unique group of order 5. Namely, you just take that 5 cycle. So if you take x, you take the cycle, you take identity x, x squared, x cubed, and x to the power 4. So I'll call this subgroup H sub x. Now this H sub x, it has 4 5 cycles. All these powers of a 5 cycle will be 5 cycles and the identity element. So there are 24 5 cycles. Therefore, S5 has 24 divided by 4, 6 subgroups of order 5. Because these 24 5 cycles, 4 of them are in one group. So 24 by 4 gives 6. And now what you do is you act on this 6 cycles. So now you let S5 acts on this set HX, where X is a 5 cycle. So this set of 6 subgroups. So this set just has 6 elements. By conjugation, that is, sigma dot hx is sigma hx sigma inverse, which will be another such group of order 5. And so if you think of these 6 subgroups as, and you number them 1, 2, 3, 4, 5, 6, then this gives rise, and it acts on this transitively. So this gives rise to a transitive action of S5 on the set 1, 2, 3, 4, 5, 6. So this gives a way of thinking of S5 as a subgroup of S6 that's very different from what we are used to, namely just permuting the first 5 elements. It's a transitive action of S5 on the set 1, 2, 3, 4, 5, 6. Okay, so I haven't been looking at the chat, so maybe it's time to look at the chat. There's a lot of stuff on the chat. Yeah. Okay, a darker pen choice would be better. Let's see. What is my pen choice? Blue. Okay, I was using gray in the beginning, so I think I've already fixed that. Hopefully, you can see better now. Okay, let's see. Okay, so there's a question from Poruri. Is this class anyway related to or will be useful for the GRE exam? It will definitely be useful for the advanced GRE exam in mathematics. Let's see. There's a question from Promila. Will you please explain how to construct permutation group on 4 elements? Okay, so I'll come to that, and then there are a couple of questions by Prasad. How to visualize, how can I relate it with real life applications? So let's see. So maybe first I'll go to Promila's question, and the question is, I'm not sure exactly what the meaning of the question is. How to construct permutation group on 4 elements? I can just so this is a group that's going to have 24. This is going to have group permutation group on. Okay, actually, what is the meaning of this? So, what is the meaning of a permutation group on 4 elements? So you have a set 4, which is a set of 1, 2, 3, 4, and we have already the group S4, which consists of sigma from functions from the set 4 to the set 4, box 4, such that sigma is a bijection. And this has 24 elements in one line notation. So, so what you can do is you can write this sigma 1, sigma 2, sigma 3, sigma 4. So they're in one line notation. So you can just list all possible rearrangements of the numbers 1, 2, 3, 4. This is where the one line notation really comes handy. It's very easy to enumerate everything without missing out anything. So I can just list them in dictionary order, for example, 1, 3, 2, 4, 1, 3, 4, 2, as if these were words in a dictionary where the alphabet is 1, 2, 3, 4. And so in this way, you can kind of see after each thing, what is the next word that should come. So after 1, 3, 4, 2, I've kind of finished everything where I have 1 and 3 in the first 2 places. So I must put 1, 4, and then I have 2, 3, 1, 4, 3, 2. And now I've finished everything with 1 in the first place. So I'll have 2, and then 1, 3, 4, and there'll be 6 things starting with 2. 2, 1, 4, 3, 2, 3, 1, 4, 2, 3, 4, 1, 2, and so on. I can keep writing 2, 4, 3, 2, 4. Well, I'm getting addicted to this, but there'll be one more column where there'll be 6 things starting with 3, and then there'll be 6 things starting with 4, the last of which will be 4, 3, 2, 1. So you'll get 24 of these. So here's how you can list all the elements in this group. And then you need to figure out the group structure, which means how do you multiply 2 such permutations. So for multiplication, the notation that is most useful is the arrow notation. So for this, for example, let's take this element 2, 1, 3, 4, then we can write it using arrows as follows. So 1 goes to 2, 2 goes to 1, 3 goes to 3, and 4 goes to 4. And suppose we want to compose it with 2, 1, 4, 3, then we will again write this. I've explained this in the lectures already in great detail. So I'll just quickly tell you, you just follow through the arrows. So if you have 2143, it looks like this. And if you want to compose these two, then you just follow through the arrows and you sort of do something like this. And you get the permutation. 1 goes to 1, 2 goes to 3 goes to 4, and 4 goes to 3. So I hope that answers your question. Okay. So, yeah. Okay, so there's a question about how to visualize and how can I relate it with real life applications. So group theory has a lot of real life applications. Whenever you have an object with some symmetry, you try to understand how it behaves by using that symmetry. So for example, if the symmetric group Sn is a symmetry of just n identical objects. If you have n identical objects, in the protons in the nucleus of an atom, then they have complete symmetry, and the symmetry group of such things is just Sn. But like in benzene, a benzene molecule, it has a hexagonal shape with 6 carbon atoms. And its symmetry group is actually of order 12. It's the dihedral group D6 of order 12. So whenever you have structures with symmetry in real life, to analyze them, you can use group theory. And for example, in spectroscopy, the kind of wavelengths that a chemical molecule absorbs is determined by its group of symmetries. So it has a lot of applications. Again, in relativity, there's a group of symmetries of space-time which plays an important role. In Newtonian mechanics, there's the group of rigid motions which plays an important role, and so on. So in quantum mechanics, there's a Heisenberg group which plays an important role. So these groups occur everywhere. In the theory of Diophantine equations, there are Galois groups which help you solve Diophantine equations or show that you cannot solve them by radicals. Okay, there's a nice question by Preeti Kumari. How many homomorphisms from Z20 to Z8? So let's see if we can solve this problem. Let's just so by Z20, I suppose you means what I call Z mod 20Z, and Z8 is Z mod 8Z. So if you have a homomorphism phi from Z20 to Z8, then if you know where phi of 1 goes, then you know that phi of 2 will go to 2x, phi of 3 will go to 3x, and so on. And there's, of course, one constraint that phi of 20, well, but in Z20, phi of 20 is phi of 0, but this will go to 20x. So what you need is that 20 times x is congruent to 0 mod 8. So what you need is that 20x is equal to 8y for some 1. So what we're asking is, so the number of homomorphisms from Z20 to Z8 is equal to the number of elements x in Z8. That means elements mod 8 such that (20x) is congruent to 0 mod 8. And if you divide, this is the same as saying that 5x is congruent to yeah, I guess I could say that 5x is congruent to, is even. If 5x is even, then 20x will be divisible by 8. Okay, so but you want 5x to be even, but that's the same as saying that So 5x, that means 5x in Z mod 8 is even modulo 8. Or rather, 5x has an even residue modulo 8. But since 5 is odd, this means that x is even modulo 8. So this is the same as saying that x has to be congruent to 0, 2, 4, or 6. So the number of homomorphisms from Z mod 20 to Z mod 8 is 4. Here's a exercise you can try. The number of homomorphisms from Z mod M to Z mod N is GCD of M. GCD, or sometimes called HCF of M. So 20 and 8, the GCD is 4, and that's also the number of homomorphisms. And the basic idea is this, that if you so in this case, you can, if you're not sure why these last two steps are equivalent, you can just try it out by hand and see which elements between 0 and 8, when you multiply by 5, they're even. Give even residues mod 8. Giving an even residue mod 8 just means that 5x is even. So if 5x is even, x has to be even. Yeah, that's it. Okay, so I hope that answers that question. Okay, so let's see. Okay, so Indrajit Devnath has a question. Can you please explain why the stabilizer of 1 in D4, let's see, in the graph gamma. So let me see if I understand this question. So if I remember correctly from lecture, I had this situation where we had this graph gamma, which had 4 nodes, 1, 2, 3, 4. I think this is the graph. I'm not sure which. Oh, no, this must be the graph gamma in the assignment. Okay, so that's a tricky question. Okay, so we have this beautiful graph. So this is not gamma. I think Devnath's question, correct me if I'm wrong, refers to this graph. Okay, this is a nice question. So it has 6 vertices and I think 12 edges. And this actually is the graph associated to a Platonic solid called the octahedron. And so now the question is, if I look at all the automorphisms of this graph that fix a point 1, so I'm not allowed to move this, then what are they? Now in this graph, there's some, so the intuitively the thing to understand is that if you have a graph automorphism, then it preserves all the relations in the graph which you can define in terms of edges. So for example, this edge, this vertex 1 is not connected, is connected to all other vertices in this graph except for the vertex 4. Okay, so this and this somehow, with respect relative to 1, 4 is somehow special. Okay, so if you have an automorphism of this graph, so it preserves the edge relations, and if it fixes 1, it will also fix 4 because 4 is the only vertex which is not connected to 1. So, okay, so your graph fixes 4 and 1. And so let's somehow, these are not really in the picture so much. So that leaves these other 4 vertices now which we are allowed to move around. And these themselves together form a graph. And if you imagine this to be a 3-dimensional, I wish I had a model of an octahedron somewhere. Yeah, I don't know if I have one. So if you take, so let me see if I can pull up a picture from somewhere. So you can visualize this as an octahedron, which is basically two pyramids, two pyramids with square bases glued to each other. So the upper one involves 1 and then the vertex is 2, 6, 5, 3, and the lower one involves 4 and the vertex is 2, 6, 5, 3, and they're glued to each other along the square 2, 6, 5, 3. And so what you can do is you can take this object and you can rotate it. You can rotate it by an angle of 90 degrees. So what I'm talking about is a permutation, but purely graph theoretically. If you don't want to think in 3 dimensions, 2 to 3, you take 3 to 5, you take 5 to 6, and you take 6 to 2. So that is a rotation. And that's a rotation of 90 degrees, so it's of order 4. So if I call this guy X, then ort gamma contains identity x squared and x cubed. Okay, but yeah. But there's another thing I can do. Let's see. So I said it's a D4, so that means I should also be able to reflect. And indeed, so for example, what I could do is there are 4 reflections. You've studied D4, right? So it's let me just draw it with only these things: 2, 3, 5, 6. In some sense, these connections with 1 and 4 don't really give you any additional structure here because, everybody is connected to 1 and everybody is connected to 4. So there's no this thing. Instead, I actually have 4 axes of reflection. I have the horizontal axis, the vertical axis, and then I have these 2 diagonal axes. So I have this permutation which just interchanges 3 and 6. So I can write it in cycle notation as 3 interchange 6, keep 2 and 5 fixed. That's the reflection about this diagonal axis over here. I have this permutation 2 and 5 that preserves this diagonal axis passing to 6 and 3. Then I have two vertical and horizontal reflections. These are in cycle notation. So if I interchange 2 and 6 and 3 and 5. So 2, 6, 3, 5. And the other one is the vertical flip, namely 5, 6, 2, 3. So there's 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. What? No. 7, 8. That's just one element. And this is D4 indeed. You just visualize it like this. Instead of 1, 2, 3, 4, you visualize D4 as the graph with vertices 2, 3, 5, 6. So yeah, I kind of rushed through this in my lecture. I was hoping that you would spend some time thinking about it. I guess yeah. Okay, so I hope that answers Indrajit's question. That's a great question, yeah. And one sec, Chandan. Chandan Kaur has a question. Discuss how you constructed ORT S, particularly for S3, seeing it as a graph. I don't really understand this question. What is S here? I don't really understand. S3 is the automorphism group of a triangle. So I don't know if that's what you're referring to. Okay. Shudipto, so I'm not sure what the question is that Chandan is asking. Maybe you can try to clarify again. Meanwhile, let me see if I can understand Shudipto's question. Shudipto is asking, can you explain the form of the quotient group Q mod Px, where Px is x cubed minus 2x minus 2. I don't really understand what is x here. Q is a set of rational numbers. We should be taking something, a subgroup. I don't see a subgroup here. So again, I don't understand the question. Boidehi Chattopadhyay has a question. Let me see if I missed it somewhere. Boidehi, I don't quite see your question. Is it? Oh yeah, there it is. Okay, okay, great. Yeah, can you help in computing the number of Sylow P subgroups in GLN Z mod P? Oh God. Okay, so yeah, so I kind of know the answer to this. But yeah, I don't think I want to attempt that right away. But basically, the Sylow P subgroups of GLN Z mod P are all conjugate to the group of upper triangular matrices, strictly upper triangular matrices, with ones on the diagonal. So you need to figure out how many such things there are. So the normalizer of this group is going to be, okay, I think I can figure out the answer to this, but it's a little involved. So let me just explain. You can use the orbit stabilizer method. So, but okay, there's still some issue. Let me just explain what I can think of right now. Yeah, so So, really done Sylow P subgroups, and we haven't really done, we don't really know. This is a somewhat more advanced question, but let me just give you a hint. Okay, so I probably wouldn't fit into this part of the course yet, but it's a great question. So GLN Z mod PZ. So what this is a group of all n by n matrices with entries in the field of all invertible n by n matrices with entries in the field Z mod PZ. So, an example of a Sylow P subgroup here is something like this: 1, 1, 1 on the diagonal, anything for the entries above the diagonal, and 0 here. This is the Sylow P subgroup. And all other Sylow P subgroups are conjugate to this. So you just need to figure out what is the group sub. So now G acts on this, GLNZP acts on these Sylow P subgroups by conjugation. And so you just need to figure out what is the group that stabilizes this. And I've worked this out sometime in the past, and basically it is the group of all upper triangular matrices where these guys are non-zero, the diagonal entries are non-zero. So that's usually denoted B. And so the number of Sylow P subgroups will be the index of B in G. I think, Vishwanath will correct me if I'm wrong. So I'm not going to, this thing is a bit, maybe it doesn't quite fit into this part of the course. We'll be doing Sylow theory next week, and maybe we'll come back to this. This is a great example for Sylow theory. And this is a really beautiful group. So it's worth thinking about this a little more. But here's a hint. So see if you can fill in the steps. Okay, so Chandan talking about the automorphism of a 4-point graph. So Indrajit has already answered Chandan's question, but it seems so. So the thing is, right. So let me just address Chandan's question in a little more detail. So the question. Okay, so there seems to be some. Okay, so we have this 4-point graph. What is the meaning of the automorphism group? Okay, this is a very fundamental question. So I have this graph 1, 2, 3, 4, and aught gamma, by definition, is the set of sigma in S4 such that if I is connected to J by an edge, which I will denote by I and draw a line towards edge to J, then sigma I is connected to sigma J by an edge. This is the definition of aught gamma. Okay, and you can show that this is a reversible thing here because sigma is a bijection, and that's it. That's the definition of aught gamma. And not every element of S4 will be in aught gamma. For example, if you interchange 1 and 2, but you keep 3 and 4 fixed, then it will not satisfy this property. It will mess up the edge relations of the graph. So any transformation of this graph which preserves its edge relations is in the group aught gamma. And that is the group B4, which is the dihedral group with 8 elements. So I hope that helps. Maybe you need to go through the examples, take a little more time and go through the examples once again. There are lots of such examples. So by the time you're done with the examples and the homework, I think you'll have understood this concept very well. Okay, so we're running out of questions. Uh, okay, so seems like we run out of questions. There were lots of nice questions. Thank you all. I hope you will stay with the course to the very end. Uh, I don't know if feedback is always good, so please fill out the feedback forms. Uh, Try to solve the assignments as quickly as possible so that you can move on to the material in the future weeks. Uh, these assignments are designed to familiarize you with the different concepts. So don't wait for the, of course, they've given you a lot of time to solve these problems, but don't wait for that. Just finish them off so that you're ready for next week's material. And I'm really, it's first time I'm teaching on NPTEL. It's really nice to have so many students. The next session will be conducted by my colleague Vishwanath in 3 weeks. Oops, one more question from Megha. Please explain about conjugacy. Yeah, Vishwanath is going to start next week. He gives wonderful lectures, so the wait is not long. You should look forward to next week's lectures. He will be lecturing for the next 3 weeks. So, Megha, what do you want to explain about conjugacy? I thought I already explained it in the lectures. So, is there some specific doubt that you have? So yeah, so I would suggest going through the lectures again, and you can also I should mention that there's this beautiful book we've recommended as a textbook by Michael Artin. It's called Algebra. Things are beautifully explained in there, and the other textbook, Dumb It and Foot, is also quite nice. My favorite is Michael Artin's Algebra, just because he has so many lovely examples. So yeah. So see you all. I'll be so I won't be like it'll be Vishwanath for the next 3 weeks, and then I'll come back with ring theory. Should we follow the textbook for reference? You should if you want. I mean, so I'm not teaching. We're not teaching out of the book as such. So you won't find that the book corresponds to our lectures really. We are trying to, again, but in some sense, in spirit, we are close to Artin's book in the sense we want to do a lot of examples, but they are different examples. So you should look at Artin's book, I think, very much because he has different examples and beautiful examples. And also, I think problem solving is very important. So I don't know how much time you have, but if you have a lot more time, then try to solve the problems in Michael Artin's book. That would take you a long way. Yeah. And also use the internet, use Wikipedia, use Stack Exchange. Look at examples. That's the main thing I would say. Yep, Michael Artin. Algebra. It's yeah. I have it somewhere here.